Okay, so for those of us joining from the future, this is Final 5, question 1B on an exponential decay in an electrical circuit. So we're going to look at charge, current, and voltage in this, what do you call this? RC circuit, resistor capacitor circuit. So the capacitor in the circuit below initially has no charge. Hang on, sorry, I'm adjusting my chat. There we go. Initially has no charge. At time t equals 0, the switch is closed and the capacitor begins to charge. Qualitatively, draw three graphs below, starting at time t equals 0. The first graph is for the charge on the capacitor, indicate the maximum charge. The second graph is the current on the resistor, indicate the maximum current. The third graph is the change in voltage across the resistor, indicate the maximum voltage. All right, so it's an RC circuit. So the first thing I want to do is recall some things about exponential decay in an RC circuit. So the first thing that I think about is that the time constant of an exponential circuit is just R times C. The time constant dominates how long it takes to charge, how long it takes for things to happen, basically. So the time constant is a unit of time. It tells me that the larger the resistor, the more slowly current will flow. So like the more time it will take to transfer the same, quote, volume of charge. Oh, the capacitance is a measure of the willingness of the capacitor to store charge. So the higher the capacitance, the more charge it can store. In other words, like the more volume of charge will need to be transferred before we reach equilibrium. So increasing either of these increases the amount of time it takes for my circuit to charge. Question about the time constants. In the context, feel free, if you're typing, please do keep typing, but in the context of an equation, as a reminder, an exponential decay looks like this. I've got an initial value and then exponentiated to the negative t over tau, which is the same as lambda t. Lambda is 1 over tau. Okay. I'm going to keep on moving in. So if I want to talk about the maximum charge in the resistor, I can use the definition of capacitance. So far in terms of like important equations, there's this one. And this is a good relationship to know, but it's not strictly necessary for the problem. The other one that I like is, oh goodness. Oh yeah, capacitance, the definition of capacitance. So capacitance, I said earlier, is basically a measure of willingness of a capacitor to carry charge. Capacitance is Q over delta V. Q over delta V. Double check myself. If I increase my C, I increase either Q or I decrease the voltage required to keep the same charge. Yep, okay, that looks good. So if I want to find the charge at the end, Q max is going to happen when I've got the capacitance times delta V, and it's when the voltage absorbed by the capacitor is all that there is. So it'll be at the point when there's no current, so the resistor is carrying no voltage, and the change in voltage across the capacitor will be everything, the entire battery voltage. So Q max is when I have the capacitance times the battery voltage. So to give a little bit more intuition for this circuit, if I make a loop around it, the only two circuit elements which absorb voltage, absorb here I mean use, are the resistor and the capacitor. So they're going to split it. Whatever voltage the resistor doesn't use, the capacitor will use. And yeah, whatever voltage the capacitor uses, the resistor won't be able to use. So I express this by saying that the battery voltage, I mean, you can use our law. So battery voltage plus change in voltage across the resistor plus change in voltage across the capacitor equals 0. Or the sum of the two changes will be equal to negative battery voltage. That's how I think about it more intuitively. Okay, I got a new message. Let's see here. Would it be a positive or negative epsilon for delta V of the capacitor? Okay, good. So during a charging, because of my direction here, because I'm going from, let me write this in, because I'm going from the positive end to the negative end of the capacitor, this delta V will be a negative number. This will be a negative number across the capacitor here. So again, like why is that? It's kind of like if I go across a battery in the wrong direction from positive to negative, because my current is flowing this way, and because I've drawn my loop in the same direction as the current, um, I'm going from the positive side to the negative side of the capacitor. That's going from positive charge to negative charge. So it's a decrease in voltage, decrease in voltage. Does that help, Sophia? So this is all about how I define my, current. And I'm right now defining my, like the arrow of my loop is always going in the same direction as the current. So if my arrow of my loop is always going in the same direction as my current, when I go from the positive side of something to the negative side of something, the voltage drops. By contrast, when I go from the negative side to the positive side of the battery, my voltage increases. So hopefully that helps a little bit. It's kind of like going up a pump versus the wrong direction, down a pump, so to speak. Are QT and change in voltage across the capacitor effectively the same thing? They're going to be similar, yes. So yeah, so we'll get there in just a moment, but well, actually, so change across the capacitor versus resistor is different, but yes, so the change in voltage across the capacitor is Q over C, right? So the Q versus T graph and the voltage across the capacitor versus T graph are going to have the same shape. One's just going to be taller than the other because capacitance is going to scale it. This constant capacitance is going to either multiply it by a big number or multiply by a small number, depending on the size of the capacitance. Yeah. Thanks, Ben, for the question. Okay. So here we are. We've got Qmax is capacitance times battery voltage. So I'm going to go ahead and write that in just so I know the asymptote on my graph. So Qmax is C times the battery voltage. The capacitance of my capacitor is 2 farads. So this is going to be with numbers. This is 2 farads times the battery voltage of 12 volts. That's going to be 24 coulombs. Whoa, that's not a 4, that's a V. 24 coulombs. Okay. Cool. So 24 coulombs. Nice. That's actually a lot. A 2 farad capacitor is very large. So 24 coulombs is like a ton of electrons or a ton of charges. Okay, but so now I can write this. Initially, my capacitor is uncharged. So part of the reason I basically know that initially because they tell me so. Initially has no charge on it. So it's initially uncharged. Q on the capacitor is 0. Cool. And after a half-life or two, the charge will equilibrate to 24 coulombs. It's actually more like 6 or 7 half-lives is when I say it's properly equilibrated. But so I'm going to go up here and mark 24 coulombs. They tell me to make it qualitative, but I'm going to put 24 coulombs anyway, just so that, I remember. Okay, so there's a half-life, here's another half-life, here's another half-life, and so on. I'm just going to mark these to kind of make it so that my graph looks good. So the first half-life will take me halfway. The second half-life will take me another half, down to 25% remaining, then 12%, then 6%. All right, now we're getting close enough that I'm going to get lazy. There we go. And it just flattens out around 24 coulombs. So there's an exponential curve. I want to be sure that across these graphs, I use the same values for time. So I'm going to mark in all of my little half-lives here. Okay. Sophia asks, is Q always positive? So it's kind of a hard one. This is okay. So here's the nuanced answer is that you can always, the less nuanced answer is that you can always choose to define things so that Q is always positive. I would say that for our purposes, Q will be positive on a capacitor, like the Q that we're interested in is the Q on the positive plate of the capacitor. So since the positive plate always accrues like positive charge, I'll say it's always positive. In situations where I charge it multiple different ways, so like say that I charge it this way and then I flip the battery around so that this side becomes the positive plate, and I ask you what's the charge on the top plate as a function of time, I can imagine Q going negative there. So maybe that's not clear. Let me write it. So here's a battery and here's a capacitor. And I ask, what's the charge on the top plate? And then I flip the battery around and ask again, what's the charge on the top plate? Well, now the negative end of the battery is attached to the negative, now the negative end of the battery is attached to the top top plate of the capacitor. So that one's going to accrue a negative charge. So both sides accrue charge. When I graph Q, what I'm doing typically is, or when someone says, tell me what Q is on the capacitor, it's usually assumed that I'm talking about the positive charge, the charge on the positive plate, the charge on the positively charged plate. There we go. Poof. So unless it's kind of a tricky problem where I'm asking you about the specifics of which plate acquires which kind of charge, Q, it's fair to treat Q as positive. If you want to be really specific, you could say Q is a positive number that is the charge accrued on the positively charged plate. And you can always just say that at the end of your question. So like if you say Q is negative, you can be like, yeah, well, that's just the Q that is accruing on the negatively charged plate. That's fine. Yeah, thanks for the question, Sophia. Okay, so there's my graph. Again, to call out the half-life. So in the first half-life, I go halfway from my initial point to where I'm going to end up at 24 coulombs. So that would be 12 coulombs, but I'm not gonna get too specific in marking it. In the next half-life, I go another halfway. So I'm now 6 coulombs away, then 3, then 1.5, then like 0.75. All right. I think we may have seen this charge graph before, so that one might not have been that interesting. Let's talk about current next. So we're interested in the current through the resistor. We're interested in the current through the resistor. Now, just to kind of like draw a connection to the rest of the circuit here, this circuit is all the same loop. And you might be like, yeah, duh, Adam, that's obvious. But when we get to voltage, it's going to change up a little bit. So it's all part of the same loop. So the fact that it's all part of the same loop means that there are no junctions, which means that the current through the resistor is the same as the current through the capacitor, which is the same as the current leaving the battery. So all of those currents are going to be the same. Why? So again, this is kind of like the fluids where there's a notion of continuity. Current can't just disappear because it's charge per time. We'd be destroying or creating charge out of nothing. And that's not allowed for like energy / mass conservation reasons. So, or just charge conservation generally is the more, okay. But anyway, so you can't just create or destroy charge. It needs to come from somewhere. So the currents in all of these circuit elements are going to be the same once the switch is closed. So let's draw that in. What is the current through the resistor going to be? Well, we should probably think about a couple of things. We should think about the voltage through resistor. We should think about the current in the capacitor. So let's think about the current in the capacitor first. So the current in the capacitor is just dq over dt, So dq over dt, and per dl, I'll just appeal to dl. It's negative dq over dt. So in the context of a capacitor discharging, it's negative dq over dt. I made a minor error in the lectures, so I apologize for that. I stated the appropriate definition for current, but then actually drew my drew my graph the wrong way. So I'll give a message about that in a minute. But okay, so the point is that, hang on, this is capacitor discharge. In a capacitor discharge, we actually maintain the positive sign of current. So we're going to keep current flowing in the positive direction around this circuit, which lines up with our choice of loop. So for a discharge, we'll go with this negative sign, negative dq over t, the rate at which the charge is leaving the capacitor. For a charge, when we're charging a capacitor, we want to maintain the positivity of current. So I'll say this is when we charge a capacitor, we keep it positive. So the reason that I've made that sign change is basically just a conventional choice. I've chosen it because I want current to be a positive number. What it corresponds to is making sure that my current is going in the same direction as my battery. Making the current it's going in the same direction as my battery. In the context of a discharge, I'm making sure that my current is going in the same direction as the discharge from the capacitor. And I can take more questions about that too in a second. Let me first just draw it though. So initially, I've got a relatively steep slope here for current. So current is positive. Then it becomes less and less steep in the upward direction. So still positive, but getting smaller towards zero. So this is going to be another exponential decay. But now it starts at a positive value because the current is initially pretty large. The slope of Q versus T is relatively large. And then over time, it decreases. So I'll draw in my first half-life. Boom, that looks pretty good. Now my second half-life takes me halfway there again. Then halfway again to zero. Then halfway again, whoa. Then here comes halfway again. And then we're pretty close to there. I'm just going to draw it nearly on top. All right. So if I want to talk about the maximum current, now I have to think about my circuit a little bit more intuitively, or a little bit using a little bit more of my basic, quote, basic physics knowledge. So there's my circuit. I'm going to go ahead and lock everything just in case I need to erase here in a moment. So there's my circuit. Now, initially, when the capacitor is uncharged, it essentially acts as a wire. It doesn't eat up any of the voltage produced by the battery. It doesn't eat up any of the voltage produced by the battery because it's uncharged. There's no charge to produce resistance, so to speak, an artificial resistance from the charges pushing against one another. So at time t equals 0, when charge is maximized, when there is effectively no contribution from the capacitor, the circuit essentially acts like a battery connected to a resistor. So to make that super explicit, let me write out this version, let me write out this version of our conservation law, this Kirchhoff's voltage law, in terms of time t equals 0. So at t equals 0, we've got the change in voltage across the resistor plus the change in voltage across the capacitor still has to equal negative the battery voltage. Now, at time t equals 0, the capacitor is uncharged. So let's see, how do we want to write this? Let's write it like this. I'll say, so negative IR minus Q over C equals negative battery voltage. So I'm just subbing in the appropriate values there. So at time t equals 0, the capacitor is uncharged. So Q equals 0. So that goes away. 0 since Q equals 0 at t0, at no time. Okay, so it's essentially, again, like the equation is identical to that of just a battery connected to a resistor. So if I want to calculate the current at t equals 0, I is just going to be battery voltage divided by resistance, I max. So the battery voltage divided by resistance is just going to be, what is that? Is that 12 volts? I believe it is, and I just covered it up. Hang on, let me double check myself here. Yep, 12 volts and 3 ohms. So this is a 12-volt battery and a 3 ohm resistor, which yields a current of 4 amps. 4 amps. Okay. Good stopping point. We got questions? Questions about current?
Could you go over the signs again about positive and negative?
Yeah, sure. So This is just a sign convention that we're setting, but the convention that we're setting is that current should be positive for like a charging or discharging interval of not QR, sorry, that's different, of an RC circuit. So during a discharge, here we go. During a discharge, what I'm talking about when I say dq here, the change in Q, is the change in charge as it leaves the capacitor. So a charged capacitor attached to a resistor is the situation that this version refers to. Just a capacitor attached to a resistor. So if the positive end of the battery is up here and the current is flowing around this way, then the charge on this capacitor is dropping over time. The slope is negative over time. So if I want to talk about current as a positive flow of charge around the circuit, this is the way that I would define my current. So again, the reason that I've slapped the negative sign out front is to cancel out the fact that slope is negative for a discharging capacitor. So this is to cancel out the fact that slope is negative on current or on charge for a discharging capacitor. Hopefully that makes sense. In this case, we're losing charge. So if we want to talk about current as a positive number, we have to multiply it by a negative, multiply the charge per time by a negative number to make it positive. Meanwhile, in the charging case, now if I'm talking about dq over dt, well, my capacitor is accruing charge. So since it's accruing charge, since it's getting more and more charge on that positive plate, the slope of charge over time is a positive number. So current will be positive already. I don't have to modify it with a sign. So I'm choosing these signs in order to like keep my current positive, which again is just a choice that I'm making. It's a choice that I'm making because it makes my life easy. That way I don't have to think about the sign of current down here, for example, because I know it's just always positive.
So then is that graph in the negative quadrant? Is that why we
Which one?
like just in general, like if we're talking about a discharging circuit and current, the graph starts in the negative quadrant and then approaches 0. Is that correct?
So good. So you're referencing the lecture, I think, right, Lauren?
Yeah, I think so.
Okay, good. So yeah, I actually need to go back and make a more, I made a note of errata on the YouTube video, but I should go back and make a more detailed note. So I drew that assuming the same like direction of current, so like clockwise. If I were to remove the battery from the circuit and let the capacitor discharge, it would go counterclockwise, which I called negative. But I actually was inconsistent in my notation that way either. So okay, so the direct answer to your question is we will typically change our notion of the direction of current to make current positive. So the current should live in the first quadrant. Yeah, and that was just a notational mistake that I made. And I'll be sure to, send out a message with a little bit more details too on what part of the lecture that was.
Okay, thank you.
Yeah, thank you. And sorry about the miscommunication. So the funny thing is I actually wrote this definition. Here's the joke. I actually wrote this definition and then I proceeded to write as though I was using the positive version. So this is the one that I wanted, but I picked the wrong, like in my head, I made a typo. Okay. Another question is Q over C in the loop rule equation supposed to be negative? So again, for charging this capacitor, yes. So I guess I should say there is supposed to be a negative sign out front. There is supposed to be a negative sign out front. Q over C itself is a positive number. So Q here is like this graph of Q, which lives in the positive quadrant. It refers to the charge on the positive plate. There is supposed to be a negative sign out front because as I cross across, as I'm going around my loop, as I cross over this capacitor, I'm crossing from the positively charged side, the side that's attached to the positive side of the battery, to the negatively charged attached to the negatively charged side, the side attached to the negative side of the battery. And anytime I go from a collection of positive charges to a collection of negative charges, my voltage decreases. I'm going, if you like, the wrong way. I'm going downhill or uphill against the normal flow, or against what the capacitor would like prefer to do if it weren't attached to a battery. Okay, any more quick follow-ups? Otherwise, we'll hit voltage real quick. These are all really good questions, folks. Thanks. So I got a new skateboard deck. I'm pretty hyped about it. I've never had clear grip tape before. It's going to be a good time. It's going to make a feature in one of these videos. I'm sure of it. Okay. Let's hop over to voltage. So we're interested now in the voltage across the resistor. So voltage across the resistor. We're not talking about the voltage across the capacitor. Recall from our loop rule below that the voltage across the resistor and the voltage across the capacitor, they're kind of fighting for the resources of the battery. They're fighting for the resources of the battery. So the total of the two will be 12 volts, but each of them is going to split it in different amounts over time. So let's think about it just from the resistor's perspective. Let's think about it just from, there's multiple ways to think about this part especially, but let's think about it just from the resistor's perspective. So from the resistor's perspective, it starts having a bunch of current flow through it, and then over time, it gets less and less current flowing through it. And I actually don't like their choice of sign convention here. So I'm going to modify this question a little bit. We'll see if it matches with the solution. So I'm going to mark magnitude delta V across the resistor. So the voltage across the resistor is a negative number, right? Voltage across the resistor is negative. This is going to be a negative number. So what I'm going to plot is the magnitude of the change in voltage across the resistor, and we'll see. We'll see what the solution says. So initially, on the resistor, I see a bunch of current coming through me. So I absorb lots and lots of voltage. So initially, I absorb all 12 volts. All 12 volts as the resistor. Over time, that current becomes less and less and less. And I drop to 0. So again, here's my first half-life, next half-life, third half-life, fourth half-life, and we're basically at 0. So if I'm talking about the magnitude of the change in voltage across the resistor, the maximum of that is going to be just the battery voltage, 12 volts. So again, at time t equals 0, the resistor absorbs all of the voltage because the capacitor is uncharged. So the Q in delta V equals Q over T, or Q over C, is 0 at time t equals 0 for that capacitor. It's got no charge on the plates, so no voltage change across the capacitor. Now, I don't know if they were trying to be tricky here. So if they were trying to be tricky, delta V max across the resistor, now I'm not going to do this like kind of correction where I say, here's delta V max. And I'm taking only the, what do you call this? Only the magnitude. If they were trying to be tricky, then delta V across the resistor is actually always a negative number because the current is always flowing through the resistor and we're dropping voltage in the direction of our current flow. So if they're trying to be tricky, then what I need to do is either draw in a 0 like up here instead of at where you'd normally mark 0. Or what I'm going to do is I'm just going to draw underneath so I can keep both graphs. But so the voltage in time, if I keep my negative sign, if I keep my sign convention, it's just going to be like that. And then I would say that the maximum change in voltage is 0 volts. Because you know, a negative number is less than 0. All right. What I'm going to do real quick is I want to see what they did. So I'm going to hop over to Canvas and see if they have chosen to keep the sign or to not keep the sign. Ah, okay, interesting. Okay, so they keep the magnitude. Do they say any particular way? Second book of the graph is the change in voltage across the resistor, indicate the maximum voltage. They don't say anything explicit. That's really weird. Okay, so we'll be explicit. I'll let you know, for example, if I want the magnitude of voltage across the resistor. Yeah. I got a question. So for graphing, are we having to look at the magnitudes? As technically it would be negative, right? That's right. So in this case, they wanted you, perhaps this is just from whatever the instructor had said before, like, well, just graph the magnitude of things. I'm not going to say that, but I will say, like, if there's a problem and it's not clear whether I want the magnitude of voltage or the voltage, I'll be explicit about it. So at the end, I'll say something like, plot the magnitude of the voltage change. Otherwise, like if I were reading this by itself, I would read this as saying, I need to graph the voltage from some negative number up to 0. And then I would draw in this little blue curve instead. Yeah. Does that help? So as far as changes in voltage across the resistor or changes in voltage across the circuit generally, I would say indicate the direction of your loop, indicate the direction of current flow, and use that sign convention as your default. So like for me, I'm looking at this. Okay, I'm accruing positive charge. That's all good. The current is a positive number. I make sure current is positive, so I keep it positive. That's one thing that should just be pretty much generically true unless you're dealing with a really strange, like niche situation where I'm asking you to think about, I don't know, I'm asking you to think about current in a strange way. And the change in voltage across the resistor, I say, should be a negative number, which then curves up to 0. Because the change in voltage across the resistor, according to my loop choice here, would be a negative number. If I want you to just graph the magnitude, I'll say it. I've got a chat coming in. In one of the other questions for the charging, they provided a graph of dV resistor, and it started with a positive value and went to 0, which was confusing. So I think we've actually got the same thing here. So, oh, I see. Okay. Okay. dV resistor started at a positive value, went to 0, which is confusing. Oh yeah, I see. Sorry about that. So in that example, they probably also were dealing with an RC circuit during a charging, and they probably just also took the magnitude of the voltage across the resistor. Yeah. So they in that problem, I assume they also just took the magnitude. Explaining why the change in voltage decreases, I would guess that that probably has to do more with like thinking about the difference between the voltage change and 0. So in that case, it sort of makes sense to think about it as a magnitude, which is to say like, that's the wrong graph. So because the voltage is decreasing slowly to 0, I know that that voltage is going somewhere else and it must be absorbed by the capacitor. The capacitor is accruing more charge, so the resistor has to give more and more of its previously well-owned voltage to the capacitor. Okay. Yeah, so again, we'll try to be explicit. If I'm looking for the magnitude of the change in voltage across the resistor, I'll be explicit about that. Otherwise, I would typically assume this is going to be negative, as it has been in the past. Can you explain again why Vmax is 0? Good. Okay. So this is using, again, the choice of sign that I'm using here, the choice of sign that the change in voltage across the resistor is a negative number, which is what we've done in the past. It's consistent with our loop where we go from battery voltage to some, in general, lower voltage over by the capacitor. So that represents a drop in voltage or a negative number for change in voltage. So I would say typically, and this graph is getting really busy. So hang on, I'm going to get rid of my blue line here. We're going to talk about the red line instead. So the reason that I say the maximum voltage across the resistor is 0 Here we go. I'm just talking about this red line down here where I've kept my typical sign convention and said, okay, the change in voltage across the resistor is a negative number. So I'll label this one as just delta V. Not the magnitude of it, but just delta V across the resistor. So the reason I say that it's 0 is because, so 0 is greater than 12, or is greater than negative 12. So initially, the resistor is absorbing all 12 of the battery's volts. So change in voltage across the resistor is 12 volts. And over time, because the capacitor is absorbing more and more of those negative volts, so to speak, it's eating up more and more of the battery voltage. The voltage across the resistor eventually drops to 0. In other words, eventually, no more current will flow through this circuit. At that point, the change in voltage across the resistor is 0. And that's the highest value over this interval. Yeah, sure thing, Christine. Thanks for the question. Okay, so if y'all are cool with it, I've actually got one more question lined up. It's pretty quick, but I think it could be just one more good capstone. It's a fluid type problem. Yeah, could be good. I think I'll pivot over there unless there's any follow-ups for this thing. I'm glad you like the intros. I showed it to my girlfriend. She's like, ugh, I don't know. It's a little childish. And I was like, come on, it's fine. Okay. The other one I want to do is quiz 3A. So exponential change. Hello. 3A. There it is. All right. Let me pull this thing over. So we've only got about 5 minutes of proper time left. So what I'm going to do is I'm just going to give an overview, and then maybe I'll stick around for like 2 or 3 minutes, take follow-up questions. But I don't want to, if folks have to run off, I definitely don't want to give like too much unfair advantage to sticking around during problem-solving sessions. So here comes the snip. And the plot. Boom. Okay. So I'm called to imagine 2 identical standpipes connected by a thinner pipe sitting on your DL table in an equilibrium state with equal water levels of 10 centimeters in each pipe. Suddenly you lift one of the pipes by 4 centimeters as depicted in the figure here. Cool. On the plot provided below, plot the height, top of the water level as a function of time for each standpipe measured from the bottom of each container. Clearly labeled curves indicate initial and final height values for each pipe. Show your work, explain your answer. So I think I may have talked about this in office hours like a week ago with some folks, but I wanted to give a quick chat on it again. So measured from the bottom of each container is key. So the heights in each of them are going to change over time. And since they have the same surface area, the change in heights are going to be the same. So the relative difference in the change of heights, so say between the right and the left, is going to be the same as that ratio is going to be the same as the ratio of their areas. Double check myself here. It's like the inverse of the areas. I have to think for a moment. Hang on. So it's, would it be area right divided by area? No, it'll be the opposite. So it'll be area of left divided by area of right. Let's double check me here. So if I had an area on the left that was 9 times bigger than the area on the right, then this would be 9 times as big. I'd have 9 times as big of a change here. Yep, I think this should be right. All right, I have to burn time here. Click, click, click. So this is kind of just like a general rule. It's not really, personally, I don't think this is a thing that's worth boxing. The reason I say it is because the change in volume must be the same for the left as for the right. And in each case, change in volume is just delta of area times height. So yeah, so if one pipe were a couple of times greater surface area than the other, its height would drop or increase at a rate that was a couple of times lower than the other. The one that's bigger moves more slowly. That's how I think about it. Okay, so I'm interested in plotting the height as a function of time measured from the bottom of each container. I've increased the height of one by 4 centimeters. So in order for them to equilibrate, one's going to have to drop 2 centimeters. One's going to have to go up 2 centimeters. This way, water is level. Go talk to the flat earthers about that one. So this way, the water is level. Water always finds its level. All right, I'm making a little joke here, sorry. But okay, so 2 centimeters down for one, 2 centimeters up for the other, because the change in height, the initial change in height between them is 2 centimeters. So 8 centimeters for the left pipe will be my equilibrium, and 12 centimeters for my right pipe. So this is 8 for the left and 12 for the right. So right and left. All right, so initially they're both at 10 here. And they just do that. They'll have the same half-life because they are the same surface area and all that. The water level in each container after 2 half-lives is going to be 2/3 of the way, or not 2/3, sorry, 3/4 of the way there. So a half times a half gives me a quarter. So I'm 3/4 of the way there. 3/4 of the way there. So for the one that is, wait a minute. Yeah, we're good. So for the one that is the left pipe, the one that's dropping in height, it's going to drop 3/4 of the way from 10 to 8. So that's going to be 8.5 left, 8.5. So to be more explicit about that, I'm starting at 10 and I'm ending at 8. That's 2. So 2 times 0.75 is 1.5. So the change in height is 1.5 from 10 to 8.5. Meanwhile, for the right pipe, it's also changing by 2 total. So from 10 to 12. It's increasing though. So it's increasing from 10 to 11.5. And that gets me 75% of the way there. 2 half-lives, 75%, because a half times a half is a quarter. I've only got a quarter of the way remaining. Did we get 12 and 8 from 10 plus or minus 4/2? Yes. Yep, that's right. So the reason that I can just take their average is because they have the same area. Otherwise, I have to think about it a little bit more complicatedly. Okay, I want to finish up number 3 real quick, and then I'll stick around for 2 or 3 questions. The resistance of the thin connecting pipe is 2,000 kilograms per cubic or per quartic meter per second. On the plot provided, plot the current. Whoa, it's a lot of plots. Plot the current through the thin connecting pipe as a function of time. Clearly indicate the initial and final values of the current. Show your work and explain your answer. So I'm not going to rederive it, but the initial current in this 2 standpipe fluid system is rho g delta y initial. So the initial change in height divided by the resistance. So the initial current is going to be, let's see, it's water, right? I think we say it's water. Yeah. Yep. So it's going to be 1,000 times 10 times 4 centimeters. This is 1,000. Whoa. 1,000 times 10 times 0.04 meters divided by the resistance, which is 2,000. And what is that? Oh God, I've lost my calculator. Someone help me. Okay, we're good. So it's 10 times, it's going to be 10,000 times 0.04 over 2,000. That's going to be 0.2 cubic meters per second, which sounds like a reasonable number to me. Hopefully I didn't make any calculation errors. Here's current. Over time, it's going to decrease. Okay, and if I wanted to get really specific, I actually have that option here because, or wait, do I have that option? No, I don't, because I don't know the areas, do I? Okay, so since I don't know the areas, I can't calculate the half-life. However, for what it's worth, the lambda, the time or the rate parameter, which is related to half-life and time constant, all those things, lambda for a 2 standpipe fluid system is rho g over AR. All right, so these are my 2 things that I would kind of make sure you have going forward if you didn't have them already, or if they weren't emphasized already. I think we all should have seen these in BL, but it's possible that they weren't emphasized enough. Okay, so with that, I know that was kind of a whirlwind tour. This is recorded, so you can always go back and take a quick look. And hopefully I explained a little bit, at least, why I did what I did on the way. Other than that, do we have any follow-up questions? Last questions before we adjourn for the day?
Two questions. So is I not supposed to be like I initial?
That's right. Not, so when I use the subscript 0, it's kind of like shorthand for t equals 0. So I naught is the initial current. That's right.
Also, I was curious as to why delta P equals 0 in the Bernoulli's equation when it's initial.
So, oh, I see. Okay. So, okay, sure. So, there's a few ways to think about this. The way that is commonly taught is that when I'm calculating the current between points, I'm calculating the current between this point and this point. So 0.1, 0.2 here. So in that case, both are at atmospheric pressure. So delta P plus, what am I doing here? Plus rho G delta Y plus rho 1/2 rho delta of V squared equals E pump per volume minus negative or minus IR. So the change in pressure between these 2 points, 1 and 2, is 0. Rho G delta Y is negligible in this case because, how do I say this? Oh no, this is for an equilibrium system. Hang on, let's back it off. The change in pressure between these 2 points, this is kind of roughly what you're talking about, right? Are we still in the right spot?
Yeah, kind of. It's that in like when they're solving for like 0, like I equals 0, they put delta P plus PG delta Y equals 0. Instead of just only having it PG delta Y, so it's kind of confused as to why initially they can say it's 0, but at the end they say there's a delta P in there.
So yeah, let me hang on. Maybe this takes me, I need to think about this a little bit and go back. So you're asking about like in the derivation for why the initial current is what it is, why does it have this value and not plus a delta P?
It's just that in the solutions, it says that delta P is 0 initially, but in the end, like when the current's at 0, they say delta P plus PG delta Y equals 0.
That's interesting. So it depends on what 2 points they're referring to. Let me check the solution to make sure we're on the same page. Cool. Pressure. The initial current at T equals 0 between the thin standpipe. Initially, no pressure difference. Okay, cool. Yes, this is right. Okay, so I see what you're talking about. So let's talk about it. So when they say apply it at the thin standpipe versus not at the thin standpipe, I kind of just take a pick. I can either pick the pink points 1 and 2, or the surface tops 1 and 2. So in either case, boom, at point 1 here, I'm at the surface of my fluid, right? So all of the pressure at this point is due to atmospheric pressure. So, and same at point 2. So if I do it on the red side here, each of these are held at atmospheric pressure. So, so the change in pressure between them is just PATM minus PATM equals 0. In this case, if I'm looking at the change in height, or the pressure difference, if you like, the head difference due to the differences in height in this fluid system, there is a notion of pressure difference between these 2 points because the left point is at a higher point in this fluid system than the right point. So the pressure difference here, so to use like a little bit slightly language that's outside the course, the partial pressure due to the water, the partial pressure pushing up due to the water, corresponds to this rho G delta Y, this change in height within the fluid system. So that's why this term survives. Because there is a height difference between these 2 points, and they are both parts of the same fluid system in the sense that they are both, like there's a line that takes me through this fluid. They're connected. Does that help? I don't know if that's like built it up very well.
I think it does. Thank you.
Yeah, sure. If you like to think about it in the context of these two here, so down here in this fluid system, the pressure at each of these 2 points caused by the water overhead plus whatever the atmosphere is giving us, the pressure at those 2 points is the same initially because we're equally deep in the fluid in either case. However, there is an additional notion of pressure here caused by differences in height within the same fluid system. So what I would say is, like, if you took, here's the ground truth. If you were to take a pressure gauge and you took a pressure gauge and you stuck it down here, during this non-equilibrium process of equilibrating, I would expect to see that the pressure down here is momentarily lower, like it's the same value in either case at 1 or 2 initially. And then over time, as this one fills up, your pressure at this lower point is going to increase. So regardless of how you phrase it, whether you think about it as a pressure difference caused by a difference in height or as a difference in a change in height with no corresponding like difference in atmospheric pressure, the numerical result is still the same. You'll still get out the same thing that's driving the current to flow, which is rho g times the change in height. And I think that's about as much nuance as I can put on it, at least on the fly.
Thank you. I have to
Yeah,
go,
sure thing.
so thank you.
Yeah. All right. I'm going to go ahead and end it here. Thanks for tuning in, everybody. And I'm going to go ahead and stop the recording. I got a chat from Ben. I had tech difficulties this morning, couldn't take a quiz, will be up for later. So for individual technical difficulties, we're just going to rely on the drop system. However, if you do have more than 2 technical difficulties and you're like at risk of taking a 0, definitely do let me know and we'll make some kind of accommodation. Yeah.
I have
Okay.
a quick question.
Oh, sorry, am I interrupting someone?
Oh, no, you can go ahead.
All right, thank you. I was really hoping, I've never said I've been hoping to take a quiz before, but I was hoping to take this quiz so I could know how like I'm doing with this material, and now I didn't get to take it, so I was hoping to at least look at it.
I will go ahead and I'll port it over to a practice quiz, so it will still be available to take as though for a grade. So it'll still be like, as long as you stay fresh on it and nobody tells you about it explicitly, you'll still be able to take it as a practice quiz fresh and see how you're doing, and solutions will be available.
Perfect. I know I wasn't getting a grade on it, but thank you.
No worries.
I have a quick question.
Go for it, V.
So for the practice exams,